Okay, so hello everybody. Now if you know Monty Python, it's time for something completely different. So yeah, my talk is about my main research activities, which focus on investigating one of the properties of the most elusive particle that we know of, which are neutrinos. And usually characterizing a fundamental particle basically means answering some simple question, like is it charged, what is its spin, and of course, how much does it weigh? Okay. And neutrinos are interesting and fascinating for many different reasons. For instance, they are the most abundant massive particle in the universe that we know of, but they don't interact very easily with matter. For instance, one single neutrino can pass through the entire Earth without making a single interaction. And this makes the detection and the characterization of this particle an extreme challenge. Perhaps the greatest advance in particle physics over the last decades has been, alongside the discovery of the Higgs boson, of course, has been the discovery that at least 2 of the 3 neutrinos have non-zero masses. However, despite years of measurement, we still don't know the exact value of their mass. What we do know is that their masses lies between 10 to 50 millielectron volt to around 500 millielectron volts, which means they are at least 1 million times smaller in mass than the electron. So we are left with this quite peculiar picture here. Here you can see the distribution of the mass of all the known fermions. The fermions are fundamental particles. And you can see that the charged ones are evenly distributed along 5 different order of magnitude, while neutrinos occupy a lonely region in this plot. So you have this gap. Why there is a gap? We don't know, but we think that could be something very interesting hidden in this plot. And probably measure precisely the value of the neutrino mass could help us to explain this unsettling gap, and also to explain, or maybe to prove or disprove, many different cosmological theories. So yeah, how do you weight a neutrinos? You can use cosmological data. You can try to study very rare and hypothetical kind of radioactive decay, which is called the neutrinoless double beta decay. But if you want to measure the neutrino mass in a true model-independent way, which means that you only assume energy and momentum conservation, you need to perform what is called a direct measurement. In a direct measurement, what you do is that you study the radioactive decay, beta or electron capture decay, of an isotope, and you record the energy released during the decay. Then you focus on the last part of the spectrum, and as you can see, in the last part of the spectrum becomes distorted by the non-zero value of the neutrino mass. So if you can detect this distortion, you can infer the value of the mass. However, please note that this distortion is very, very tiny. So in order to perform a robust measure, you need to do multiple measurements with different techniques, with different isotopes. And at the moment, there are 2 main research lines. One which studies one of the isotopes of the hydrogen, which is the tritium, and the other one which studies one of the isotopes of the holmium-163. Okay, so to detect such a small variation in the spectrum, you need to record the energy released during the decay in a very precise manner. And what we do, we embedded the radioactive isotope, in our case the holmium-163, inside very tiny detectors, 300 micron in size, cooled at almost absolute 0.1 Kelvin. These detectors are called TDS, transition rate sensor. They are superconducting detectors. They are thermometers working in the narrow temperature range between the resistive and the superconducting state. And in this range, a small variation in temperature causes a big variation in the electrical resistance of the film, in such a way that even a single decay of an atom, which causes an increase in temperature, can produce a detectable signal. So in this picture here, you can see the order which shows 64 of our detectors. These are these little a square here in the middle. And actually, due to the fact that the detectors are so small, our experimental setup is very compact. We can put all of our detectors inside this machine here, which cools our device at cryogenic temperature. And if you want to compare, this is the size of just one part of the detector that it usually uses in this kind of measurement. So yeah, I work in this experiment called Holmes, like the detective. And last year, we performed our very first measurement of this isotope using this technique. And as I was saying, forget about everything, just focus on the last part of the spectrum. We performed a fit of the last part of the spectrum, and we were able to infer a limit on the neutrino mass of about 35 electron volt, which means that the sum of the masses should be lower than 35 electron volt, which proved the feasibility of this technique, and for us was a great achievement. So let me conclude. In the next year, we will try to continue our R&D to design an experiment that could exceed the sensitivity of the current state of the art in this matter. But as physicists, we usually tend to prepare for the worst, according to the Murphy's law. So the worst case scenario in this case is that one of the three neutrinos has 0 or close to 0 masses, which means that the sum of their masses should lie above one of these two green lines. However, as a takeaway message, I want to paddle upstream and tell you that this is an exciting moment for our community, because on one end, we are getting closer to one of the lowest limits on the neutrino mass. But on the other hand, if we were able to find the neutrino mass in this energy range here, it would create a tension with one of the most famous cosmological theory, which is lambda cold dark matter. And when there is a tension, usually in physics, there is something interesting, because that means that we have to rethink about the description of the universe that we know. So thank you. And